Hello. In this occasion, we'll explain the concepts of data and multimedia data linkage on the semantic web. This is based on the Linked Data Initiative. The participants of this investigation are Kevin Wong and Freddy Ramirez. The agenda is as follows. First, we'll see the introduction. Is data on the web interlinked? Second, we'll see linked data and semantic web. Then we'll see accessing linked datasets. Then we'll see what are in-clouds. Then we'll see how to link data. After that, we'll see the multimedia data and its metadata. Then we'll see multimedia content, how to make it more reusable and findable. After that, we'll see how to link multimedia data. Then we'll see multimedia fragments and how to link those fragments. And finally, we'll present and propose some conclusions. Okay, now, for an introduction, is data on the web really interlinked? As of now, web pages offer the possibility to create links between them. In this example, we see that the first page is connected to the second one following a link. However, once inside, we realize that information displayed is independent and does not possess a way to automatically relate to the other content. This is because content in the web, the HTML content, is made so that human beings can read it, and not machines to understand its semantic implications.
Linked data and semantic web. But what is linked data or what is semantic web? Linked data is simply about using the web to create type links between data from different kinds of sources. On the other hand, semantic web is a web where the information is linked. So we will use linked data techniques to make a semantic web. Linked data. First, interlinking data. It's the first thing that we should think when we talk about linked data. There are several methods where we can do it, and we are going to talk about them. The indefinite navigation from any start point. It means that we can from any start point, which is a linked entity, navigate to many related entities, following URIs specified inside the visits entities. By last, everyone can publish. Everyone will be able to contribute with the semantic web publishing. New content that will help to make a better interlinking between different kinds of data. Implications of linked data. There are some implications when we interlink data, as you can see. There are some implications for professional data consumers, like reduce data integration costs, reduce licensing costs, combined with organization internal data, and also cross-domain use. Also for end users, richer, more up-to-date navigation, better detection of context, and better context-related offerings. Linked data principles. These principles should be respected in order to make a right linked data. First, use URIs as names for things. It means that we should start using URIs when we want to refer to some piece of information. Then, use HTTP URIs so that people can look up those names. When we use HTTP URIs, it allows the user to navigate to the web to get the piece of information that is related to that URI. When someone looks up a URI, provide useful information using the standards. It means that every time people look up for a URI, they will receive useful information that is related to that URI. Finally, include links to other URIs so that they can discover more things. It means that some properties inside the entities represented at URI, so you can navigate to related entities and obtain information related to that property. In the next image, we are going to see how linked data principles works. First, we have an entity represented as URI. Then, second, we look up related information to that URI. Third, we obtain a piece of information that is related to that URI. And finally, fourth, the information have new URI that is related to a new entity. Data categories. Synode have categorized data in two data categories. First, single resource are data like URI reference or simple text. Also, there are component resources. Each component resource is aggregated by one or more single resources, like multimedia, synchronized bookmark, transcript, or presentation.
Before we continue further, it's important to understand the RDF concept. The resource description framework is basically a way to represent information. When represented as an RDF triple, it can be seen as a graph-based model. RDF can also be represented as XML format, which is the standard syntax for RDF, which is RDF XML. However, other encodes also exist. As for a triple, we can define it as a way to represent information where we specify the object, which is the current entity, and link it to another object that, for example, can be an URI, in which we use a predicate, which in this case will be the connector. As said before, the default encode for RDF is RDF XML. The syntax is, as we can see there, which is basically an extension of XML. Also, when implementing RDF in XHTML, we use RDFA, which uses a syntax that is incorporated inside HTML. RDF incorporates many vocabularies, and in order to describe their semantics, we use RDFS and O. Also, to describe their structure, we use KOS. As explained before, we have different encodes for RDF, which, for example, are notation tree, turtle, and n triples. An example for n triples is seen as follows, which define a subject, an object, and its predicate. During this topic, the vocabulary or ontology word will be used a lot. A vocabulary or ontology is basically a set of words. Each is used to describe a property for a linked entity. We could say that the used vocabulary can define the parts or sub-information units of an entity. For example, we have the Dublin Core vocabulary. Part of its set of words inside the vocabulary is, for example, the word publisher, which describes, for example, the person who published one content. We also have other terms relevant to linked data. First is the web of data, which is basically the whole space or network where linked data exists. The web of data basically consists in HTTP accesses, URIs for names, and sets of RDF triples. We define a dataset as a particular group of linked entities that are published in the same domain. These sets can be RDF stores or even relational databases. We also have the Linking Open Data project, whose purpose is to incentivize the publishing of linked data to existing datasets. For then, we can interlink the published datasets. As of now, there exist more than 200 published datasets and 20 billion triples. Now we'll talk about accessing linked datasets. One of the most common ways to access linked datasets in RDF is the use of SPARQL endpoints. First, SPARQL is a query language that is similar to SQL that is used especially to query our RDF resources. The SPARQL endpoints offer HTTP query services and the possibility to execute SPARQL queries over data set addressed by the endpoint. We have many SPARQL endpoints provided by each of the datasets provider. A complete list or an almost complete list is at the W3C webpage. It is also important to note that in order to overcome the limitation of having many specific SPARQL endpoints, SPARQL data consolidators exist. They basically do is query over many datasets instead of just one. We have an example here, for example, the OpenLink Load Cloud Cache. Now, we will review some methods to query linked data. First, we have data warehousing, which consists in the creation of a data warehouse, which is a preloaded store of information. The easiest way for this is using an RDF dump. The advantages of data warehousing is the performance of querying, since all the information is already preloaded and network operations are not required. However, this makes it more difficult to maintain the information up to date. Then, we have search engines for linked data. These are like traditional search engines for linked data, but they also possess matching techniques for RDF typos. Their way of navigation is using RDF links, indexing them, and provide query interfaces over the indexes. The downside to search engines is that it's hard to cover the whole web data, which means its precision will be below 100%. Then we have query federation. This method consists in decomposing the query into subqueries, so that it can be processed across multiple sources. This job is done by a query federator. The downside to this method is that a lot of network operations are required, thus making it a slow process. The advantage of this approach is that no additional storage is required, nor the necessity to synchronize data in the process is required. The author also proposes two novel query approaches. The first is active discovery based on query federation. This one is an enhancement to query federation, which includes active discovery of SPARQL endpoints during the query process in order to enrich and alter query patterns during runtime. This helps the problem of small data coverage. And the other method is link traversal based on query federation. This other method is also an enhancement to query federation. It basically adds the possibility to navigate through links inside the RDF data in order to find possible related information to the original query.
Properties. As you can see, there are 8 query approach properties that are universe of discourse, required source interface, access to original data, supporting data structures, response and throughput, recall precision, and up-to-dateness. In this comparative table, you will see the data warehousing, search engine, query federation, active discovery query federation, and link traversal that are different kind of characteristics from these properties.
An important concept when accessing linked data is the use of content negotiation. For example, we have the bird-song resource, which can be expressed as information or as raw audio. Content negotiation basically does a redirection when asking for a resource, and this redirection can be specified in the HTTP request by filling the desired representation in the accept header. Finally, there are two forms of consuming linked data. First is the human consumption that consists in a linked data browser. For machines, however, the way to access linked data is by HTTP requests, which will return an RDF. In order to parse RDF files, many parsers exist. We have, for example, the Jena Semantic Web Framework for Java, the RDF lib31 for Python, the same web 32 for C#. Also, in order to use Sparkle, some APIs also exist. For example, the ARC33, the Wrap34 for PHP, the Sparkle Wrapper 35, the PySparkle 36 for Python, and finally Jena for Java. We also have Sparkle consolidators, which basically access our many datasets, which are the ARQ, SemWQ, and SUclip.
Now in clouds. Linked data clouds. An in-cloud originates from a set S of linked data extracted from a repository R from a combination of SPARQL queries that are kind of queries for RDF graphs. Techniques that are used. Linked data matching are employed to discover or the pairs of similar resources in the set S. Linked data aggregation invoked to determine an in-cloud by putting together those resources of S that are characterized by a high level of similarity according to the matching results. The ways to show linked data in clouds depends on some kind of filtering and the details of the users. Filtering in clouds. First, by content. Allows users to restrain the exploration of a considered in cloud to a subset of concepts that satisfy a given user interest. Also, users use a series of keywords to determine user interest. It means that the user will filter in clouds with some keywords that they want to know or learn about. Filtering by relevance allows users to restrict the exploration of an in-cloud to those concepts that are more relevant with respect to prominence and proximity requirements. There are two kinds of filtering in relevance, as we mentioned before. Filtering on prominence allows to select those concepts N that have a prominence P higher than a user-specified threshold. Filtering on proximity allows to select those proximity relations that have a degree of proximity x higher than a user-specified threshold. In other words, these techniques transform an in-cloud A in an in-cloud B. Displaying in clouds. Visualization of the in-cloud depends of the user's detail through filtering by content and filtering by relevance. Users select the elements that wants to display from every kind of in-cloud. The in-cloud visualization can be focused on showing only the concept essential of the results, which give a better knowledge of the selected topics.
Now, we'll talk about how to link data. Linking data basically is the identification of equivalent resources. The purpose of this is, for example, finding ontological identity, which means the same real-world object, logical identity, which means two objects can be replaced in a sentence, or a formal identity, which means basically an entity or a digital identity. The uses of linked data is to connect data in order to form links or to find duplicate entities in some datasets. In order to match data, we use instance matching. The types of matching is one, comparing the data, or using knowledge provided by, for example, ontologies. Matching techniques can be classified in three ways. One is value matching, which basically compares the values inside entities. For this purpose, we can use string matching, we can use keyword-based search engines, or use external knowledge sources, for example, linguistic resources. Then, the other granularity level is individual matching, which basically matches two entities. For this, we aggregate the values resulting from value matching. We can use pre-existing identity links, already formed links, or use external repositories. Finally, the granularity level of dataset matching. This basically uses already matched datasets or uses two different datasets comparing similar relations to entities between them in different datasets.
Linked data properties. Linked data requires some properties to is satisfied. That depends typical design and characteristics of linked data sources. First, the capability to select linked data features for matching. The goal is to reduce the number of features to match, thus simplifying the overall execution cost of classification, by also avoiding to detect similarities that are irrelevant for the considered aspect view of the data. Second, capability to detect the causes of similarity. A similarity value between two linked data is caused by one or more feature matchings, namely type, property name, or property value. So, similarity value usually provided by a state-of-art matching tool is not capable of capturing the causes of similarity. By last, capability to support matching results with a measure of confidence. Given a similarity mapping between two linked data items, a sort of confidence measure is required to capture the reliability of the mapping. On one side, this notion of confidence needs to provide a quantitative measure of reality. The sense is that a certain similarity value is more reliable when it is based on a high number of matching properties, value that rather than one on single properties or value.
Then we'll talk about multimedia data and its metadata. Multimedia data is hard to find because multimedia data don't use the same representation for its metadata. Thus, it's difficult to understand a property in one vocabulary when matching it with a different vocabulary with different names for its properties. Also, the metadata inside multimedia comes from many sources, and there's even non-readable representations of data. Another problem to communicate multimedia is that its metadata is represented in different vocabularies, which are not compatible one with each other. For example, in the image presented here, we have EXIF metadata for a multimedia object, which doesn't understand the terms used in Dublin Core, ID3, or MPEG-7. As said before, metadata comes from many sources. These include the ones that are created when the file is created. When professionals annotate multimedia and when users annotate, this means that multimedia metadata must be variable over time. These sources are classified into authoritative, which is the creator of the content, and non-authoritative, which is the changeable metadata added after its creation by any user. Also, we must note that multimedia must support many non-authoritative sources, which means that many metadata can be added after its creation. The most common metadata types for multimedia in the web are identified as follows. We have bibliographic metadata, technical, metadata for classification, in order to evaluate multimedia, relational, which relates to other resources, information related to rights, and metadata that describe functional properties. We must also take into account some factors to make multimedia more findable and reusable in the web, as it is hard enough to find for its complexity. Now we have the definition of a good metadata model. A good metadata model must provide content description that can be used for search engines. It must also be able to capture all information and content related to social features. The model must be designed so that it can interoperate in different communities. And finally, it must support the change or addition of new vocabulary. We also have the possibilities to publish multimedia data as RDF. For that, many wrappers exist. Those wrappers are specified in the following link. Also, we have wrappers that wrap many file formats, for example, the Aperture framework, or we have wrappers consolidators, for example, TripFS. These wrappers consolidators basically take many wrappers for individual formats and put them together. We must also take into account the most common ontologies used in the web to represent multimedia. These are, for example, Dublin Core and Dublin Core terms, FOAF, or friend of a friend, basic geo vocabularies, music ontology, Creative Commons, review vocabulary, and ontology for media resource. These web vocabularies also include some not so widely used. For example, the multimedia metadata ontology, the core ontology for multimedia, video vocabulary, and the W3C EXIF vocabulary. In order to link multimedia to more information, relevant data sources must be known, which are as follows. For example, the DBpedia dataset, the BBC Programs and Music, DBTune, linked movie data, geonames and linked geodata, and FOV profiles.
How to link multimedia data. Interlinking multimedia. Interlinking must follow linked data principles. Interlinking multimedia should follow the same principle of the normal linking data. For this purpose, interlinking must follow linked data principles. Then, in interlinking process, all kind of provenance information must be used in order to provide a wider field of information. Also, all the metadata must be considered in a standard ontology, so that can interoperable all whole multimedia descriptions. Interlinking methods. There are some methods to interlinking multimedia data. By first, automatic interlinking can be applied in situations in which quality metadata information is available that can be used to identify objects and their semantics. Then, emergent interlinking, also known as semi-automatic, can be based on the principle of emergent semantics, whose underlying principle is to discover semantics through observing how multimedia information is used. Third, user-contributed interlinking, also known as manual. The advantage of the application of UCI for the interlinking of multimedia is that it is based on end users as sources of qualitative information. Fourth, game-based interlinking, also manual. This is related to UCI, but the difference is that the game-based interlinking is oriented to interlinking helped by game. Users are not aware that they are interlinking multimedia data. Finally, semantic wikis, collaboratives. Everyone contributes to create new related URIs like a traditional wiki.
Now, one element in multimedia that is very relevant to users and information linkage are fragments. Many times, information is associated to part of a resource, and in order to have more accurate linking addressing, fragments are important. A fragment is part of a multimedia object, which can be of two types: spatial, like in images, or temporal, like in audio or video. In order to be able to use fragments in an interlinked environment, fragments must be represented by URIs. Many methods exist to present fragments in URIs. First is URI queries and /namespaces. Then we have hash namespaces. URI queries and slash namespaces have problems, which are that servers don't host the fragments. This can sometimes lead for errors like not found files or not found resources. Then we have hash namespaces as a better approach, even though it also poses some problems, which are that some formats have undefined fragment semantics. A syntax for fragment URIs is defined by the W3C, which is based on hash namespaces. We have an example here, which defines the URL of example.com. This defines the frame of duration and the space which will be presented for this resource. We also have the concept of annotation, which follows a similar mechanism to fragments. However, they have a different purpose. It is basically a description of a multimedia object, defined as a separated URI. It could be described as an attachment to a multimedia, like social tags in an instance. We have already some existing annotation models. For example, the Limon, which uses MPIG-21 media pointer schemes. We have the W3C Media Fragments Working Group, which is a media format independent fragments addressing by using URIs. Then we have the multimedia metadata ontology, and some others like Teletask, DBpedia Mobile, Loader, etc. Then we finally reach some conclusions.
Conclusions about linked data. Linked data propose an easy way to navigate through a global network of information. Also, web of data is quite developed, however, multimedia support is still immature.
Then, the conclusions about multimedia. In order to interlink multimedia formats, a global mapping between ontologies is required. This is because using cross mappings can create a problem when scalability is required. This standard ontology mapping should support all levels of information provenance. After that, normal linked data matching methods can be applied between multimedia using a standard ontology. It is also important to note that multimedia can then interact with the web of data in order to enrich its information.
Conclusions for fragments. In order to interlink fragments and URI are proper information representation is required. Also, fragments should be linked to their parents. And finally, annotation works in a similar way as a fragment. I hope you have understood perfectly our presentation about data multimedia data linkage. Thanks for have listened us.